Thank you very much. So what I thought I'd do with this 10-minute slot is really give you an overview of Microsoft research, focusing in particular on our lab in Cambridge, UK, which you can see in this beautiful building here. Really to give you a sense of the scope of our research and also some idea of the culture and what it's like to work at Microsoft. Just to begin at the top, really, Microsoft, as I'm sure many of you are aware, has undergone a tremendous transformation in the last few years, led by our new chief executive, Satya Nadella. And you see here our mission statement, empowering every person and every organization on the planet. What that means in practical terms, if you're interested in machine learning research, is that we connect with and collaborate with essentially every kind of industry and every kind of organization that there is. And so there are tremendous opportunities to work on fascinating and large-scale data sets from many, many different domains, as you'll see as we go through. This transformation, and I'll make a personal comment here, is something which causes me to be enormously proud to work at this new Microsoft. And I'll just give you one example. This is an announcement that we made as a company a few days ago, in fact. This is a very audacious and ambitious goal for the new decade to become a carbon negative company. Now, just to be clear, Microsoft has been a carbon neutral company since 2012. That means every time we emit some carbon dioxide over here, we do some offsetting over there to balance it out. This is a much more audacious goal. This is a goal to achieve by the end of the decade, genuinely being a carbon neutral, a carbon negative company. That is, will not simply offset carbon emitted here with some offsetting scheme, but instead ensure that the net carbon that we emit to the environment is actually negative. And then an even more audacious goal by 2050 to remove from the atmosphere all of the carbon that Microsoft has been responsible for emitting since the company was founded. So this is a very audacious and extremely challenging goal, the first company to announce such a goal. It may even involve the creation of some technologies that, as it were, have yet to be invented, but compared to Kennedy's audacious goal of landing on the moon by the end of the decade in the 1960s, in a sense, we have a much better starting point in terms of the availability of technology. And also, this is very challenging. It's also something which I think demonstrates tremendous thought leadership. And there are many, many other aspects to this as well, including providing great transparency about the carbon chain, as it were, involving both downstream and upstream, so that there's high visibility about where carbon is being emitted. So turning now to Microsoft Research, we have labs around the world. Cambridge, UK was the first lab to be established outside of the US some 22 years ago, and we now have labs around the world. The mission of the lab is to transform the world through deep research. So what does that mean? Well, first of all, each of these words is carefully chosen. The goal is to have impact on the world, that is, impact at a global scale, impact at a Microsoft scale. My own view is that we have a very privileged position. We're well-resourced, we have incredibly smart people, and we connect to billions of people via the vector of Microsoft. So I think we even have a moral obligation to think at that global scale. We don't just want to be incremental, we want to make transformational advances. I'll say more about that later. But we don't just want to do this through the application of machine learning. That's important. There are lots of applications of machine learning being developed across Microsoft. But in MSR, we want to do this through the vector of deep research. So we want to tackle problems which have at their heart very difficult research challenges. So we organize our lab into various themes, and this is a little bit of a brief overview of some of the major themes of the lab. I'll start with cloud infrastructure. The cloud, of course, is the next wave of computing technology. Microsoft is a major cloud player, and we're looking at technologies that can not just incrementally improve, but actually transform the nature of the cloud. So the cloud comprises data centers, and as the name suggests, one of the things that data centers do is to store data. Data has been stored for many, many decades in the form of magnetic domains. Today, long-term archival storage of data is done on magnetic tape. Magnetic tape is a fine technology, but one of the challenges is that it doesn't last very long. Every few years you have to rewrite the tape because the domains move and the information decays. The trouble is the amount of data in the world is growing exponentially. It's doubling every 2 years. So tape technology is just rapidly going to become infeasible. This is a radically different approach to long-term storage of data. This is Project Silica. And the idea here is to make use of some very new physics that was discovered a few years ago at the University of Southampton, by which data can be stored inside glass using extremely short pulses of light, femtosecond pulses of light that creates these mini diffraction gratings that allows data to be stored with high density. We've been developing this into a practical technology. The person here is holding up a block of glass that contains the entire Superman movie. So this is a collaboration with Warner Brothers. On the left, you see the Superman movie as it's stored today on a physical plastic medium, and it's just one of the challenges of industries like the media industry is this long-term storage of incredibly precious material. There have been examples of fires that have destroyed thousands of historic films, and they don't want that to happen again. The glass storage technology has one property in particular that's very interesting, which is that it should survive for thousands, if not millions of years. It's impervious to all kinds of influences, and unlike magnetic tape, doesn't have to be rewritten. So that's an example of technology which doesn't just incrementally improve existing technology, but provides a radically different approach. Those of you who came to my talk yesterday may remember that I mentioned this extraordinary exponential growth shown by the red curve here in the amount of compute that you have to apply in order to achieve the state-of-the-art in machine learning. It's an exponential growth at a doubling time of about 3.5 months. That's a factor of 10 per year. This graph is from OpenAI. It's about 18 months old now, but that graph has continued along the direction shown by the red arrow. So the latest GPT-type language models sit on that curve. They require enormous amounts of compute, and they deliver enormous benefits. This really is a breakthrough, a revolution in natural language processing. Everybody's very excited to try and stay on that curve. Let me just show you that from a different point of view. This is an indication of the scale of model that we're able to train if we have a certain amount of compute. So the GPT-2 model that I referenced there had about 1.5 billion parameters. And so you can do a very simplistic comparison with the number of synapses in the brain of various organisms. And so that's at about the level of a bee. We've gone about a factor of 10 since then. An interesting question is, when do we get to the level of human? There's no suggestion, by the way, that simply building a neural network with the same number of connections as there are synapses in the brain gives any kind of artificial intelligence, but it's just an indication of what point do we get to the same scale of compute that corresponds roughly to the brain. And it's a staggering number, by the way. So this is a map of the Amazon rainforest to give you just some idea, and to give you an idea of scale. That's the United Kingdom, which for some strange reason seems to have become detached from Europe and floated off into the Atlantic. I don't know quite why that's happened, but anyway, the red outline is the Amazon rainforest. The number of neurons in the human brain is of the same order as the number of trees in the Amazon rainforest. But what matters, of course, is not the neurons, it's the connections between them, the synapses. The number of synapses in the human brain is of the same order as the number of leaves on the trees of the Amazon rainforest. Just to give you some idea of the staggering number of connections in the human brain, there's now this aspiration to build artificial neural networks that have comparable numbers of connections. We're about 5 orders of magnitude, 1, 2, 3, 4, 5 orders of magnitude away. Actually, today we're more like 4 orders of magnitude. It will be interesting to see how long it takes us to get there, and it will be particularly interesting to see what new emergent properties arise as we hit each factor of 10, in the same way we've seen these remarkable properties in natural language that have arisen with the last factor of 10. Another of our themes is healthcare intelligence, the application of machine learning in the domain of healthcare. This is a project that we've been working on for several years. It's called Inner Eye. We're using deep neural networks and attention mechanisms and convolutional nets to analyze three-dimensional medical images, in particular to be able to segment the normal organs and also tumors. This has various applications. It's used for radiation therapy planning. If you want to treat a solid tumor with radiation, You have to target the radiation at the tumour, miss and avoid the vital organs. That's a three-dimensional optimization problem. But to solve that, you need a map, you need the outline of the tumour, and you also need to know where all the vital organs are. So this is technology which allows radiation oncologists to perform their job more accurately and a lot more quickly. Yesterday we talked about our collaboration with Novartis, and one of the projects we're working on is the use of that 3D image analysis technology for treating age-related macular degeneration by analysing 3D images of the retina obtained through optical coherence tomography. Briefly then, Station B is our relatively new initiative, just started a few years ago, where we bring together biology and computer science, and in particular we're trying to use techniques from computer science to make the field of synthetic biology much more systematic. The goal ultimately in the long run is to produce a compiler for biology. You specify a phenotype, it will give us the genotype. That's the long-term aspiration. In the meantime, we anticipate lots of practical applications of this, but I'll just show you a rather frivolous thing we did. We opened a wet lab a couple of years ago, and as a little warm-up exercise, we used computational techniques to work out a sequence of DNA, single-strand DNA, which when it's cooled down would fold up and self-organize, and it was designed, 3 different segments designed to fold and self-organize into the logo MSR. So that wasn't done by positioning each atom one at a time. That was done by self-organization on the basis of a computational process. Confidential computing addresses a very important area. In machine learning, data is, of course, at the very heart of machine learning. We want data at scale. We want to bring together data sets from different sources. At the same time, we want to preserve the confidentiality and privacy associated with that data. And confidential computing is a technology which ensures that data remains encrypted at all times, except inside the chip where it's decrypted for computation. And that means that nobody, not even Microsoft, can access that data unless they have the key, and the key is held by the owner of the data. And that's actually been deployed in Azure, currently the only cloud that currently supports that technology. And a great application of that in machine learning is the ability to bring data together from several different providers, pool the data, train machine learning models, provide the trained model in such a way that each data provider is unable to access the data from the other. And then my final slide, the most important thing, of course, we have in our lab is our people, and we're growing in a number of fields, not least, of course, machine learning, and in domains like healthcare. If you're interested in positions, whether it's internships, PhD scholarships, residency programs, postdocs, engineering positions, research positions, please come and talk to us. We have a booth out in the main hall. And with that, thank you very much.